Hello everyone, welcome back to my channel. I am Ganesh studying BE Second Year Computer Science in Sri Venkateswara College of Engineering. Today's video assignment is on the subject data structures and applications in C programming. The topic is on the computability of relaxed data structures, which are queues and stacks as examples, which is taken from the research paper of Springer Journal. Firstly, abstract. Most concurrent data structures being designed today are versions of known sequential data structures. However, in various cases, it makes sense to relax the semiotics of traditional concurrent data structures in order to get simpler and possibly more efficient and scalable implementations. For example, when solving the classical producer consumer problem by implementing a concurrent queue, it might be enough to allow the dequeue operation by a consumer to return and remove one of the two oldest values in the queue and not necessarily the oldest one. We define infinitely many possible relaxations of several traditional data structures such as objects, which are queues and stacks, multisets and registers, and examine their relative computational power. Next, the computability of relaxed data structures. Here, queues and stacks and their practical implications in concurrent computing are studied, where the classical producer consumer synchronization problem by implementing concurrent queue to return and remove one of the two oldest items in the queue and not necessarily the oldest one as if usually required. More generally, in some cases, it makes sense to relax the semiotics of traditional concurrent data structures in order to get more efficient and scalable concurrent implementations. Next, introduction. Traditional versus relaxed data structures. In this paper, we investigate the compatibility of weight-free relaxed data structures by considering infinitely many possible relaxations of several traditional data structures and objects, queues, stacks, multisets, and registers, and examine their relative computational power. Our results demonstrate, for example, that for a concurrent queue, small changes in its semiotics dramatically affects its computational power, and that similar results do not apply for a concurrent stack. Traditional versus relaxed data structures. The distinction between traditional and relaxed data structures lies in their approach to memory consistency. Traditional data structures guarantee strict consistency, ensuring that all reads and writes to memory are performed in a sequential order that is visible to all threads. This guarantees that data is always consistent and predictable. Relaxed data structures, which sacrifice strict consistency in favor of performance. They allow for some degree of non sequential memory access, which can improve performance in certain scenarios. However, this also introduces the possibility of race conditions where different threads may observe different values of the same memory location at the same time. The some more differences are memory consistency. In traditional it is strict and in relaxed data it is relaxed. Performance. In traditional it is generally slower and right side it is potentially faster. Race conditions. In traditional no, in relaxed data structures it is possible. Use cases. In traditional we can use for general purpose programming. In relaxed data structures we can use for performance and critical applications to design. Next, consensus numbers. A process executes correctly its algorithm until it possibly crashes. After it crashed, it executes no more steps. A process that crashes is said to be faulty, otherwise it is non-faulty. The definition of consensus numbers: it is the measure of computational power of data structure in solving consensus problems. The binary problem is to design an algorithm in which all non-faulty processes reach a common decision based on their initial opinion. The problem is defined as follows. There are n processes p1, p2 up to pn. Each process pi has an input value xi belongs to 0, 1. The requirements of the consensus problem are that there exists a decision value v such that 1. Each non-faulty process eventually decides on v, and 2. belongs to x1, comma x2 until xn. In particular, if all input values are the same, then that value must be decision. Relaxed queues and overview. First queue, we can take list generalized queue with relaxed NQ, DQ and peak operations. Relaxing the NQ operation. It is obvious that CNQ101 equal to infinity list. Each process inserts its input value into the queue using an NQ operation and then uses a peak operation to find out what is the value at the front of the queue and decides on it. Also, it is obvious that for an unutilized queue, we show that only when the NQ operation can insert a value at an arbitrary position, the conscious number drops to 2. Otherwise, in all other possible relaxations in which the NQ operation is supported, the consensus numbers is not affected, E, which is infinity. Relaxing DQ and peak operations. If the queue is not empty at X, then after the two NQ events by P and Q, the adversary can force every peak event to always return. Relaxing DQ. Here consensus number drops when DQ operation is relaxed. In relaxing peak, drastically changes the computational power from infinity to 2. In relaxing peak, it is not possible to decide which process NQ event was first. Thus, it cannot be that both events are NQ events, a contradiction. Q's difference with stack. Stack. It represents the collection of elements in last in first out, in queue first in first out. Objects are inserted and removed at the same end called top of the stacks. Objects are inserted and removed from different ends in queue. Insert operation is called push operation in stack. Insert operation in queue is called NQ operation. Delete operation is called POP in stack operation. Delete operation is called DQ in queue. In stack there is no wastage of memory scope. In queue there is wastage. Plate counter is example. Relaxed registers. It is common to assume that operations on the same memory location are atomic. They occur in some definite order. Lamport has defined three classes of shared registers which support read and write operations. Practical implications. In databases, cloud computing and parallel processing, various optimization enable reordering memory references as it allows much better performance. When a correct operation depends on ordered memory references, memory barriers are used to prevent reordering. Without using memory barriers, as a result of reordering, a read from an atomic register may obtain some older value when compared to value this would read written in the order of the original program code, when compared to the value it would return in the order execution. In two constructions, we present two constructions of registers by indicating how write operations and read operations are performed. A register can be either a single writer or a single writer multi-reader. The first construction implements a single writer multi-reader, K-safe or K-regular. Lastly, conclusion of the topic. Here we study relaxed data structures, offer enhanced scalability and performance in concurrent computing. Our results demonstrate somewhat that each one of the infinitely many relaxed objects considering has one of the following concerns. In exploring the computability of relaxed data structures like queues and stack, the study highlights their flexibility in operation while maintaining essential properties of performance in concurrent situation and environment. Lastly, thank you for watching this video. Please watch the full video and like it. Thank you.